Calling civil action 18-5982 Echevarria et al. Versus Facebook Inc. and related cases 18-6022 Bass Jr. versus Facebook Inc., 18-6172 McGuire versus Facebook Inc., 18-6246 King et al. Versus Facebook Inc., 18-6263 Benditoes et al. Versus Facebook Inc., 18-6511 Wick versus Facebook Inc., 18-6583 Menezes versus Facebook Inc., 18-6657 El Qasem versus Facebook Inc., 18-6887 Melodez versus Facebook Inc. et al., 18-6953 Schmidt versus Facebook Inc. Counsel, please step forward and state your appearances for the record.
Good morning, Your Honor. Ariana Tadler, Milberg Tadler, Phillips Grossman, on behalf of the plaintiffs.
Good morning, Your Honor. My name is John Yanchunas of the law firm of Morgan & Morgan. I filed the Echevarria and Walker case. Thank you.
Morning, Your Honor. Andrew Friedman with Cohen Milstein Sellers and Toll. Also for the plaintiffs, we filed the Menezes case.
Good morning, Your Honor. Douglas McNamara, Cohen Milstein, colleague of Mr. Friedman. Thank you.
Good morning, Your Honor. Ryan McGee, and I'm with Mr. Yanchunas' group at Morgan & Morgan. We filed the Echevarria and Walker complaint.
Anyone else on the plaintiff side? Okay, on the Facebook side.
Good morning, Your Honor. Andrew Klubach, Latham & Watkins, LLP, on behalf of Facebook.
Okay.
Good morning, Your Honor. Elizabeth Dealey, on behalf of Facebook, also with Latham & Watkins.
Good morning, Your Honor. Sarah and Turner, Latham & Watkins for Facebook.
Okay, thank you. Welcome. We're here for two things. One is the tutorial, which we'll get to in just a second, and the other is the case management conference, which will immediately follow. My law clerk will hand out to you multiple copies. I don't think I have quite enough for both sides, but of a tentative schedule that is a little brisker than the one you suggested. And I'll give you a chance to argue with me over it when we get to the case management part. But I wanted to give it to you now so that maybe at our first break you'd have a chance to look at it and take your Pepto-Bismol for your heartburn so that you will be all ready to go whenever the case management conference starts. All right, so welcome to the court. Here's what we're going to do. We're going to teach me some things about this problem. I want you to know I do not have a Facebook account. I want you to know, so I have some general idea about how social media accounts work, but I feel like it's unethical for judges to have Facebook accounts. Because one of you lawyers might try to be my friend, then I would be in trouble, wouldn't I? So I'd just avoid that problem. I do think there's I do think I understand the generalities, but I want to learn about it. Also, I want to learn about hacking. So there we are. That's why we're having this tutorial. So each side has 60 minutes to hold forth and educate me. Who on this side would like to speak first?
Good morning, Your Honor. Again, my name is Ariana Tadler from Milberg Tadler Phillips Grossman.
Say your last name again.
Yes, sir. It's Tadler, T as in Tom, A, D as in David, L-E-R.
I don't have it on here. Maybe I do. But I have so many names. Where is it? Oh, here it is, right here. Yes. Tadler.
Tadler with a T. Yes, sir.
I got it. Okay.
Thank you,
All
Your
right,
Honor.
you go first.
Well, I'm just going to do a quick kickoff. At council table, you have three firms, my own, Milberg Tadler Phillips Grossman, Morgan & Morgan, and Cohen Milstein. Excuse me. Collectively, we have worked to put together the tutorial for this morning. We have some experts who will be here to talk about a variety of issues that are responsive to the questions that you posed in your order for purposes of today's tutorial. And in addition, there are quite a number of people in the courtroom who also represent plaintiffs and have filed some cases in this matter, and this has been a coordinated effort with support
Well,
from
they should
many of
make
those
their
folks.
appearances if they're counsel in the case. Are any other people here who want to make appearances? I think you should put your name on the record. Okay, now we're doing this by FTR, correct? And this is being recorded, but I need for you to say your name, but since it's on a tape recorder or digital recorder, we need, so say your name again.
Thank you, Your Honor. Joshua Watson from the Arnold Law Firm, working with Mr. Yantunis on this part.
All right, I heard that pretty clearly. Okay, yes?
Good morning, Your Honor. Jonathan Shub, S-H-U-B as in boy, Code, Swift, and Grad, Philadelphia, representing the plaintiffs.
But which particular case did you file? All right. All right, I got it. Okay, anyone else?
Morning, Your Honor. Karen Riebel, R-I-E-B as in Roy, E-L, Lockbridge, Grindle, Mallon, in Minneapolis, representing the Nexus claim.
Okay, great. Anyone else?
Good morning, Your Honor. Melissa Emmer, E-N-E-R-T, from Stone Brody, representing the Benetoes plaintiffs.
Thank you.
Good morning, Your Honor. A.J. J. Bartolomeo, D-E space capital B-A-R-T-O-L-O-M-E-O. I'm also with Millbrook Tadler, representing the White.
All right, anyone else?
Ivy Bell with Franklin D. Azar Associates, representing the Colonial plaintiffs.
Say your last name again.
No, and is Nancy G. and George Rosenbosco.
All right, thank you.
Morning, Your Honor. Dan Robinson, Magazine, representing the plaintiff, Joseph Melinda.
Uh-huh. You got to say it again. I just didn't get it. Well, no, but it also has to be clear on the tape.
On behalf of the Nexus plaintiff, with
All right. Thank you. Okay. All right. Okay, so the reason we don't have a court reporter is, I think I've been told, it's on account of the partial shutdown and the shortage of funds, but I had wanted a court reporter, but we have to do this today by FTR, the tape recording system. But that's okay. We do that in a number of civil cases, and it'll work out fine. And it's also, by your consent, someone had wanted this to be, the tutorial to be recorded. I think other judges in the country are interested in it, and so they wanted to see what you have to say. So someday a judge in a distant part of the United States may say, well, you didn't say that on the tape. What you said on the tape was X. Now you're saying Y, so be careful. This is going to be used in other cases. All right, are you ready to proceed?
I am, Your Honor. I'm actually here simply to make an introduction of Ryan McGee from Morgan & Morgan, who is going to kick off the presentation. And I just wanted to reiterate, we welcome the opportunity to educate the court and to answer whatever questions you have throughout the course of today. So
Excellent.
thank you.
Thank you for that. All right, so please come forward. And your name again?
Ryan McGee, again with Morgan & Morgan.
All right.
And, Your Honor, I have printed out hard copies of the slide deck as well as executive summaries and CVs for the two experts that we'll be calling today.
Okay.
If Your Honor would like those, I do have copies for opposing counsel, the clerk.
Well, go ahead and give me whatever you think in the easiest way that you feel is going to help.
And Judge, we're going to begin the presentation with Miss Mary France. She has over 28 years of experience in the cybersecurity field. She is the CEO of Enterprise Knowledge Partners, LLC. She has served as an expert in numerous data breach cases. She's also a certified ethical hacker. She conducts penetration testing, and she's an information systems auditor and her CV and summary have been submitted for the court today. And Ms. France will be addressing the personally identifiable information, the value of that personally identifiable information, and the industry standard practices to protect against hacking.
All right. Great.
And that will be followed by Mr. Strebe, and I'll introduce him with his credentials.
Okay, now let's have her come forward. She can stand right where you are. She doesn't have to be on the witness stand, or did you propose to do that?
We spoke yesterday with your court personnel, and they indicated the witness stand, but whatever worked for Your Honor.
Well, this doesn't have to be under oath. This is just a tutorial. I don't propose that it be under oath. If you want to do it under oath, okay, but I feel, is that all right with both sides? All right.
That's fine, Your Honor.
All right, so the expert can come forward. Still, I expect her to tell me the truth. I know she will. But she can stand right there and be the professor as opposed to the witness. Unless you want to do it a different way, I'm okay. I can absorb it any way you feel is best.
I think it'll be easiest if she sits at the witness stand. She'll have access to this.
Please take the witness stand. But again, this does not need to be under oath. So you testify as if you were a witness, but this is not a evidentiary hearing. This is a tutorial. So welcome to the court. Say your name again and use the microphone, please.
Mary France.
F-R-A-N-T-Z. F-R-A-N-T-Z.
Yes.
Okay, welcome, and counsel, go ahead.
Thank you, Judge. Now, Ms. France, one of the first topics that we've been asked to speak about today and educate with the tutorial is personally identifiable information. And I'd like you to start off with a general explanation for the court, what's meant by personally identifiable information.
Personally identifiable information in general are a series of data elements that can be combined that uniquely distinguish any one individual to the point where they can be contacted or found. And there are statutory standards by state as well as under the National Institute for Standards of Technology, the FTC, et cetera, where they have certain data elements like first and last name, address, et cetera. And California has their own version that is slightly more comprehensive than the standard.
All right. I can hear you perfectly fine, but does everyone in the courtroom, can everyone hear okay? Everyone's indicating yes. All right. Thank you. Good.
And we've provided the definition, but I'd like you to discuss the difference between what you call historical, or excuse me, what's referred to as historical and temporary personally identifiable information.
Okay. So the context is basically how it can be used and the value of it. So as from a hacking standpoint, we look at whether the personally identifiable information from an individual has a long or short life based upon its use and value and who can find it. So, for instance, temporary, what we call in our industry, temporary PII is something that can be changed fairly easily. It doesn't mean that it's any less disruptive to an individual as should it be taken. It just means that it has more or less the ability for the individual to control it. So something like a credit card. You find out your credit card was hacked, you can go get a new one, you can change a bank account, things like that. So that have limited life, so to speak, in its value. Things that are historical are things you can't change, things about you that you can't change, such as your mother's maiden name, your employment history. Your Social Security number can be changed, but it's incredibly difficult, so that usually sits within the historical aspect. Information about you that is that determines who you are, you can be identified by it, and you're stuck with it for your entire life. That has a much higher value, and that's what we call historical PII.
What was that first one called? Historical versus the earlier one was the temporary.
We call it temporary
okay.
Or maybe a limited life. The other one has more of a long or sometimes even infinite life.
Okay. All right.
And diving a little bit deeper into the value of personally identifiable information, can you explain what's meant by the term of FULZ, F-U-L-L-Z?
Well, FULZ is a slang term that we kind of use in the industry also that's meant to say almost like a dossier on you. of when, on the individual, of when we've actually gained a whole bunch of information that allows somebody to potentially create a complete doppelganger of you in the online world or even in the physical world. It also
What was
has
that word? Doppel?
a duplicate of you, so they could basically create your identity. It's not you, so they're creating a false identifier or a duplicate of
Someone did that to me. They created a fake blog, is that the word? Where they said they pretended to be me talking about the Waymo case. I think most people realized it wasn't really me, but would that be a doppelganger?
Yes.
Okay.
Yes, it would.
Right.
So, they can go online, get a picture of you that is the original picture. They can get your information, your first and last name. They can get information about your behavioral traits, how you write, and then they can actually emulate that online and pretend they're you. Well, can you imagine what happens when people who don't know it's not you, and they can get fooled by that? So fools is a little bit more broad than that. It's basically a lot of different information put together, and the more information you have on any one entity, the more valuable it is. Just because you have so much that it's really hard to dispute.
Okay. Next question.
And Ms. France, would you speak about the value of PII in general with regard to the interested parties?
Well, the highest value, again, is the fulls or aggregated information, simply because I have so much information about you. I can actually use that to manipulate opinions, influence. I can use that as an ethical hacker to do a social engineering campaign in which I can actually perform phishing exploits, because I can do something that you're so comfortable with because I know you so well. So the more information you have on an individual, more than information that's gathered on an individual, the higher the value is on the market from a nefarious standpoint, obviously. And when you are able to take a huge history of an individual's behavior, particularly online, you can get comments that they've made, you can get who their friends are, you can achieve what they liked, what they clicked on, things that they purchased, and you put that all together in kind of a package. And it can be mined to the point where whoever has that information, it knows you better than you know yourself.
And can you explain how that applies to something like challenge responses?
Well, challenge response questions are usually formatted. So are you familiar with Your Honor? I'm sorry.
No.
Okay. When you have some form of multi-factor authentication, so you don't just need a user ID and password, or when you forget a password, you can set up sometimes a series of questions.
Like your mother's maiden name.
Right.
Yeah, all right, I know what those are.
What street did you grow up on?
Right, exactly.
What was your first car? Things like that. Well, when somebody has FULS information, they can actually more easily, if not very accurately, answer those information on someone's behalf, and then be able to get into their systems. So challenge response is one of the easy ways that FULS is actually used.
All right.
And Ms. France, something we were asked to speak about is the dark web, but I'd like you to discuss the differences between the dark net and the dark web.
Well, as somebody in the industry, it's more or less a pet peeve of mine when the two get confused. But when somebody says the dark net, they're really talking about the underlying infrastructure, the machines, the relays, et cetera. And the dark web is the services that rely on top of that infrastructure. So you have a network, and then on top of that you have the browser. And the dark net and the dark web are based upon anonymity. Basically, it's used to protect the digital privacy of an individual so they can't be traced. It's used for both good and nefarious purposes. And the way the dark net works is a system of routers and relays, so that every single time somebody connects from point A to point B to get to a service, they actually bounce around quite a bit. The minimum is like 3 hops. So I'm going to connect to that machine, and that machine before I get to my source, and hence I obfuscate the trail. It's very hard to trace who I was when I started off. So that's the dark net. Is that way. It's a series of routers and relays, and the dark web is the services that rely on top of that, sort of like we see in our normal browsers. Services like email, secure email in this case, etc. And you can't really get to the dark net without using a browser or some sort of service that relies on top of it.
I don't get the difference between the dark net, which I understand what a router is, and relays and those things. But I don't understand the difference between the dark net routers and relays versus the ordinary ones that the regular internet uses. What is that difference?
The dark net actually uses the same infrastructure, but they use devices that are not registered or indexed or named, so to speak. So your regular internet, if you want to go to a website, a www.whatever, the reason why that naming convention is known is because it's been registered with the domain service, and you type in the address and you can find where you're going to, okay? The dark net physical infrastructure is a series of devices that aren't registered, they're not indexed, so to speak. You can set up your own relay on it. It's not hard to do from a technical perspective. But you don't name yourself, you don't say who you are. And so when you get into the dark web, into the browser, it's not like you can just Google something, okay, with a, look for a key term or something like that. You have to actually know where you're going. You have to know the actual address. And the addresses that you use in those browsers are not English-like. It's not like I want to look for Facebook, so I Google Facebook. It's I have to know the exact address, and the address is usually gibberish. It's actually a hash. So it's you have to be fairly. You have to know where you're going and why you're getting there. Now there are sites that have listings where you can find things because they've been gathered over time, but for the most part, it's meant for that anonymity. And it looks the same as the internet, except for, like I said, they're not registered, they're not indexed services. So you have to know what you're doing and you have to know where you're going.
Why does anyone want to be, why would anyone want an address that's just a hash number?
Well, if you're from a country that has a lot of censorship and you want to you want to be able to do what everybody else does on the internet, you want to be able to communicate and collaborate just like you would the free net or the public internet, then the method of the dark web and the dark net is to basically allow you those same services without being traced. So there's a lot of people that use the dark net and the dark web are not nefarious individuals.
So I had the vague idea that dark web was illegal, but you're telling me no, it's not illegal.
No, it's actually developed by the U.S. government, actually.
Okay.
When the internet first got started, they wanted a way to be able to use the collaboration capabilities of the concept of the internet without having their information be available to the public.
Ms. France, could you speak a little bit about how the dark web is used to traffic stolen data and stolen information?
Well, again, that's the anonymity piece. And the lack of being able to trace you, so it's enveloped based upon digital privacy. And they would use that so they can traffic without being caught. So if I steal something from you and I don't want you to trace who I am, I'm going to go to the dark web and try to find a buyer for it, that sort of thing, and hope that I'm doing it in a way, because there are ways on the dark web to be caught, but hope that I'm doing it in a way that I can still get that information and trade it and buy and sell using the currency of Bitcoin, and you can't see who I am.
Excuse me. I'd like to move on. We briefly discussed it, but have a little more of a discussion of how personally identifiable information is misused with big data repositories.
Well, remember we talked about fulls. I'm going to get as much information about an entity as I possibly can, and much of that information as it's gathered, particularly from very comprehensive sites, social media is one of them. I'm going to take all that information about an entity and I'm going to put it into a large repository. Usually they reside on what we call NoSQL structures, which I'll get into in a little bit. But very large repositories, and I'm going to hold that, and I'm going to hold that on usually either my own unique site, or I'm going to stick them out on a dark net infrastructure piece and then get to it via the dark web. But basically, I get all that information, I combine it as needed, I try to stay stealthy on the wherever I got the information from so they can't trace it back to me. But basically, the more I have and the more I can kind of trickle out there, the more valuable it is and the more money I make. Now, there's some organizations that want it for their own, to steal IP, some nation states, et cetera, but when they want to make money, sometimes they trickle pieces of that out there and they actually sell it on the dark web.
And when you said that you wanted to trickle the information, does that indicate that it's sold off in pieces instead of these fulls that you were describing earlier?
Yes, because if I all of a sudden dump everything out there that I let's say stole from somebody, I'm going to be able to take that trail, and even if I can't catch the person or the individual or entity that did it, I actually gave it away that I just hacked this company, I just hacked the organization or whatever. And what happens is that the organization all of a sudden starts to lock down. They notify their customers that you've been hacked, and people start to be a little bit more careful. So the value of it may drop for the short term. But again, that historical information stays out there forever. So my goal is an advanced, and I want to make it ethical hacker in my case. My goal is not to get caught, okay? So dumping everything out there at one time is going to cause some red flags, specifically for people who are, looking for that, let's say the FBI or something like that on the dark web. Okay, so my goal is to just trickle things out there and make it last as long as possible and never give away who I am. And sometimes I don't sell it myself. I would give it to third parties that all they want to do is get a quick buck. Another thing that we often do when
you say get the whole thing, give millions and millions of items of information to, or do you mean trickle it out to those intermediaries?
Trickle it out to the intermediaries. So let's say I steal your mother's maiden name, Your Honor, and your address, and let's say your phone number, and a few other things. So I want to make some money off of that. There's a couple ways of doing that. I only give out pieces of it, and maybe I make one piece of that completely wrong so that the value is diminished, but I'm also saving the data for later because it doesn't look like something was fully compromised, and it can't be traced. So you do that. Sort of like if I steal a car, I may sell it off in pieces, and instead of just selling the whole car, one, it's really hard to trace because not all the pieces are going to be serialized, so I can trace it back to the car that's stolen. But I also extend the value of that because I can sell the pieces off in pieces for greater than the cost of the whole. So I actually make money off of it that way. We're dealing with logical information, so the car can be duplicated all over the place. It's not a physical thing I lose at the end of the day.
Ms. France, on this next slide, we have this graphic of the high-level hacker life cycle. If you could just walk us through this, the life cycle that you've displayed here.
Well, this is a genericized hacker life cycle. There's lots of copyrighted versions out there where people have developed very in-depth methods and versions and testing criteria for this. This is a very genericized, but I want to point out one thing. The first thing that I do as an ethical hacker when we're hired to actually hack into a company is we look for what we call low-hanging fruit. So we're going to do reconnaissance scanning. We're going to monitor the environment. We're going to take a look at their websites. Okay, we're going to see what's available, and we're going to do something called crawling the website or crawling that particular service that they've exposed to the web to try and find data that we can use. And sometimes websites are built very poorly, and when someone's logging in, if you're looking close enough and you know where to look, you can actually see user IDs and passwords, tokens and cookies, et cetera, exposed. And we take that, and then sometimes that's all we need to show, hey, we can get into your website. We can pretend that we're somebody else when we're getting into it, depending on how we've crawled or exposed that particular site. Other times we do a network mapping called an Nmap. It's a common tool. It's free. But again, I'm going to do this as an advanced hacker. I'm going to try to be very quiet about it because I don't want the company knowing I'm looking at them. I don't want the entity knowing because they start to put in their own defenses and make it more difficult for me. So I become very quiet and I just take a look at it and see what I can find. So reconnaissance scanning tends to be the common denominator for the start of any type of hack. And sometimes you don't need to go farther than the reconnaissance scanning. Sometimes you get what you need and you can break into something. Sometimes you have to take more advanced steps. Maybe try to get in there and see what the error messages are so it tells me about their environment. But reconnaissance scanning is very common, and most organizations that have anything of value are constantly being tested by unethical hackers to see what they can get and where some vulnerabilities or holes may be in their services.
So let's say you have a website that lots of people use, and there's private information in there. Still, these websites say that they have secure steps taken. So I got two questions. One is, if that's true, how does a hacker even get through? And does the hacker somehow see machine language, see Java language? What is the language that the hacker sees when they're trying to bust into a system?
It depends on how well the system was built. And that's pretty much the nuts and bolts of it. I mean, if the system is built very, very well, they try as hard as they can not to expose information that would give even someone a clue as to how to break into them. If the system is not built well, then sometimes it's a free-for-all.
Well, what does the hacker see when they're trying to break into what appears on their screen?
We actually have a small, very short example of that.
Good, let's see that.
Okay. So this is a generic web crawl, and we did use Facebook, but I did not log in. And this is a free tool that you can download. It's got a tutorial with it. It's called Zap. It's free. It's been around for a very, very long time. But you see, as someone goes into www.facebook.com, all this information comes up. Now, that may not look very digestible by somebody who doesn't understand the technology, but for us, that's the first place we look when we are hired to simulate a break-in.
What is, I see those rows and columns. What does that represent? It's too tiny for me to read. I can't
When
read it.
someone goes in and types in www.facebook.com, there's a lot of stuff that happens between your browser, for instance, and the services that are being delivered to you. So this is the things that go on in the background. And now you can see them with the naked eye without using a tool, but it takes a little bit more skill depending on the browser. This is just a free tool that exposes every bit of data that's going back and forth between your computer when you got in. And it doesn't have to be, the current case. It could be anything that you get into. You can get into utility bill, to pay that, and you will see this stuff going back and forth. You click something and you try to grab that service, and it's delivering that website back to your screen, populating it based upon your credentials. Let's say you put in a user ID and password or you didn't, but it's populating that website. And so this is what's going on behind the scenes.
What page number is that in your slides?
9.
Page 9, Your Honor.
Let me see if I can read any of it. It's still too small, I can't read, I'm sorry.
We can print a copy that will be larger for Your Honor, provide it to Chambers after the hearing.
No, it's, no, but is what is on page 9, is that the Java code? Is that Java code to begin with? Is that what that is?
It could reference that. In this case, I think what it is, because I only did it for a couple of seconds, and I wasn't trying to break in anything. I was just giving a small example of what could be seen. Most of this is HTML and what is brought back and forth between the session on your browser session. So I go to a browser, whether using Safari, Google, Internet Explorer, it doesn't matter, and I type something in. What you don't see right away in your visual screen.
I never see anything like this when I do it. How do you get this to come up?
Well, I used a free tool called Zap. That's part of the a web consortium that focuses on helping people build secure websites. And they're a worldwide consortium. They've been around for 15 years. And so they produce these tools so that companies can use them for free, or individuals or whomever can use them for free, and they can see what maybe somebody from the outside can see. So they know if confidential or protected information or information that would give a hacker, a malicious hacker, a clue as to how to break into their environment. So this is a free tool. You can actually download it onto Windows and pull it up, and very simply, without any knowledge of the tool at all, just type in the website you're trying to get into, and this will show up. Now, there are more sophisticated tools, but this is a very easy free tool.
Are they on page 9, are those individual lines, do they represent the communications back and forth between Facebook and the user? That seems like that's what you're saying. So these are the details of the communications back and forth between Facebook and the user?
Yes, Your Honor, to a manner of speaking, it's really between your browser, not you in particular, but your browser and your browser session and the Facebook services, wherever they may be.
Okay, so how would a hacker use that to then hack into the Facebook system?
Well, if I'm looking at it and I wanted to see how or what information came back and forth, I'm going to put a search criteria on that, and I'm going to separate out things like things that look like user ID and password that may be passed in clear text or even in somewhat obfuscated text to give me an idea. I'm going to look for links that call out to, let's say, internal infrastructure. I may look for cookies. I may look for tokens. I may look for a lot of different things in there. And I'm going to take that and I'm going to say, aha, let me see if this works when not going legitimately into this into this particular website. We've been very successful with that type of reconnaissance scanning when we go in, when we're hired by organizations to see what can be seen from the outside. And so the screen that's up right now is actually the internal methods that companies use to protect themselves from this type of event. So the whole goal of corporations and small businesses and individuals who put stuff on the web is that they can use these types of tools and they can test themselves to see what it looks like from an external malicious hacker's viewpoint to make sure that they're not putting stuff out there that could leave them vulnerable. Because again, I'm going to be looking for low-hanging fruit. I could, as a more of advanced hacker, I'm going to go a lot deeper if I don't find it, and I really want this information. I really want to get in. But what I just showed you was a very quick and easy way. What organizations do with their own security is they use these types of tools to emulate what an external malicious hacker may see or do. So their steps are, first of all, to perform their own reconnaissance scanning from the outside in, to say, hey, what can be seen about me? Am I giving away something I shouldn't be giving away? Am I living by, let's say, my privacy statements? Did I inadvertently expose something to the internet that I shouldn't have exposed that would either leave a part of our business, the client, the whole company, or whatever at risk, okay? And then fix it. And there are ways to fix it. And there are methods and tools out there that you can continue to test to make sure you fixed it correctly. And then each step of the way, I go through this and I make sure that I'm following protocol that actually emulates. So if the slide here shows the external hacker life cycle, and then what organizations, what best practices to do internally at a very high level, I might add, to protect them from those malicious hackers.
And Ms. France, I'd like to call your attention to the next slide. The securing databases, kind of a natural segue for what you were just speaking about. Could you speak about structured versus unstructured databases?
Yes, so now there's multiple types of databases, but I'm going to talk about them in two different formats. Structured, which is what we normally see with very large mature databases and rows and columns where you have specific data elements and tools, and you can query against them so you know what's in what row and what column. You can query and find that exact cell, let's say in a spreadsheet or in an Access database or anything like that. Unstructured database is basically a repository where you can put a large variety of data in there at once, and it's meant for speed, so volume, velocity, okay, is two of the key words for that. And you'll see that a lot of the data, not only that's stolen in FULS format on the dark web, is stored in this when they mine it themselves and they put it on their own infrastructure, but also large organizations that gather data, a lot of data about individuals, either for marketing or for mining purposes, et cetera, to find more information to use that to be able to communicate with your users better, put it in these large NoSQL structures. And NoSQL is almost always open source. There are some paid versions of it, but it got started as free software. Most expensive part about it sometimes is actually the hardware and the processing units that you put it on. But unlike structured databases that they're very mature and they have a lot of built-in security, unstructured databases are pretty much open. You have to create the security mostly around them. And you very rarely find, you can, but you very rarely find encrypted data elements within a NoSQL structure simply because it increases latency, it increases the seek time to get to the data. So you see most of the security actually being around it and preventing access to it and from it, and putting it on isolated areas that you know exactly who's getting in there and who's not getting in there, and you can control that type of traffic. It's just that the goal is to have as much data as possible and make it as fast as possible. And if you start putting too much internal security, you actually slow that down. So the security tends to be on the perimeter of a NoSQL structure and not necessarily internal to it.
And Ms. Franz, would you review the best practices for the NoSQL that is on that next bullet point in the slide?
Yes, so basic things. If I were to download a free framework or something like that on NoSQL, you'll find that all the ports are open. They have known default ingress and egress ports, or how do I get in and out. So you want to do things like change those ports. You want to create access gateways to get into it. You definitely want to disallow concurrent access by the same credential getting in there simultaneously, because that means that if I stole your password, then I could use that while you're in there too. Also, you want to create logs so that you can audit that traffic going back and forth and what was taken and what was used and all that. So there's things that you build into that. Audit logs are pretty important because most structured databases have them built in, but unstructured databases do not.
And segueing from securing the databases, can you just briefly touch on securing web apps?
So we use Zap as the example when we were crawling the Facebook site there without even logging in. Zap comes from, like I mentioned, the OWASP consortium, which is the Open Web Application Security Project. And they've been around for 15 years, and their whole goal is to, it's a group of individuals that have that put out methods and ways that are just industry standard, or they set the industry standard to determine how to secure websites like Facebook, social media sites, anything that's really exposed to the internet. So they set out the standards for that. And they're most popular for what they call their top 10 vulnerabilities or their critical threats. And the top 10 started sometime around 2003, I believe. And three types of threats have been in there consistently since it started. One is cross-site scripting, which is something that I was looking at in that crawl, that ZAP crawl that you saw the example of. Cross-site request forgery and broken access control. Broken access control cross-site request forgery started in 2007 as a known vulnerability for the way current websites are being built, but the rest of them, they've been out there for almost, for over 10 years. And cross-site scripting specifically says, do that process where you're running and looking at it from an external hacker's point of view and see what's exposed. You want to look for the ability to bypass access controls, but you more importantly want to look for exposed cookies and tokens in there so that you can re-architect it, and they give you lots of different formats to how to re-architect it so that those particular items are not exposed, and therefore you can decrease that vulnerability.
And what about briefly cross-site request forgery and then also the broken access control?
Well, broken access control is when, well, it's a little bit more complicated, but basically broken access control in a nutshell, very high level, I want to add, is that I can get into that site without actually logging in. And I can steal some of those things that are exposed and then use that to access it without being tracked, without, I can bypass the normal method of making sure that someone who gets into a site is the right person and is secure.
We're going to run out of time. We've already used almost 40 minutes of your 1 hour. Let me ask you a question. Do you have a good understanding now of what you think went wrong with the Facebook situation we're dealing with? And if so, can you explain it to me?
Well, we haven't performed discovery on this from Facebook's perspective at all. So we have it from what's been exposed and knowledge in the industry from being, let's say, an API developer, et cetera, for Facebook. So we have some idea, but I do not feel qualified to talk about any type of actual details because I can't back them up yet. I don't have that discovery.
That's perfectly okay. I just wondered if you did. Okay, now you need to be aware that when 1 hour, that the time's up at 1 hour. So you got about 20 minutes.
And that concludes Ms. Fran's
All right,
presentation.
Ms. Franz, you've been very helpful. Thank you.
And Your Honor, next we'll present Mr. Strebe, and that's Mr. Matt Strebe. He's got over 29 years of experience. He's the CEO of Kinetic IT Services, also the CEO of Synergy Cloud Hosting. He served as an expert in numerous data breaches. He's authored 18 books. He is the inventor of the No Transfer NOTX patented device authentication protocol, and his CV and executive summary have been.
Thank you. All right, what's your last name again?
Strebe. And he'll be discussing authentication, access tokens, and the hacking of those access tokens.
All right, please welcome to the court, and please go right ahead.
Good morning, Your Honor. I'll speak very quickly.
All right. No, you don't have to. But when the hour's up, the hour's up. All right, go ahead.
All right. So the things that I wanted to talk about were a little bit. I want to first let you know that I'm talking generally about some security protocols and not specifically about how Facebook works because. As Ms. France alluded to, we don't actually know yet.
That's fine. That's fine. That's early in the case. I understand.
Sure. So generally in a web application, there are two big pieces of software. There's the server-side software that runs in Facebook's cloud infrastructure, and then there's the code that they deliver to the web browser that runs in the browser. That's called
now, is that browser on my desktop?
That's right.
Or is that somewhere in the cloud too?
No, that's the software running on your desktop. So
Right.
this is a case where they are delivering software to you in real time, and your browser runs it. That's the JavaScript language that you've learned about. Just to make things confusing, there's a totally different language called Java, but the one that runs in browsers is called JavaScript. So when you have a classic old-school web application, it was a very simple transaction between your browser and maybe a single server. You download a web page, maybe there's some JavaScript code in it, and it shows you on the screen what that website wants to show you. Security in those cases was controlled by a simple mechanism called a session. A session's like a phone call. When you first call somebody, you know who they are by their voice, or they identify themselves. That's an authentication process, right? They've authenticated with you, and you understand that because you're still on the same phone call, that it remains the same person. So session authentication is how simpler web apps, and especially in the early internet, did most of what they do. More sophisticated large-scale web apps that have billions of users, they have to, by necessity, use many hundreds to thousands of servers to store all the data that is stored. And so they have a problem that early mechanism of using session authentication doesn't work well for all the different pieces of data that they have to put together. And when you load a social media web page, there are elements of data that come from all kinds of different servers. It might be that if you have a friend who's in France, his information may actually come from a server that's in France because it's close to where it's normally used. That's one possible example. It's often the case that different types of information, like videos or images, are stored in even entirely separate kinds of databases that are optimized for that particular kind of object. So when you look at a social media web page, you're seeing data that comes from all over the place. And to handle that, there is a protocol that's kind of standard for internet services called access tokens. Access tokens I'm going to talk about kind of by metaphor, and with all metaphors it's a little bit imprecise. But an access token is essentially an object that has all the security information that a server needs to know about you embedded within it. That information is put there by the server before it's given to you. They encrypt it so you can't really see what it is, but it has your identity in it. It has things like expiration dates. It has some codes to make it a little more tamper-proof or uniquely identifiable. The key thing about access tokens is that once you log in, you go to a login server, it's like the security guards at the entrance to this building. Those guys are authenticating you. They take your license or your passport. They're verifying that you are who you say you are. If we extend the metaphor a little bit and said that once you come in, they hand you an access key card that gives you access to the different rooms in this building based on what your role is. That's similar to how an access token works. So when you go to log into a web app, you log in, they hand you web access tokens, and those are stored inside your web browser. A couple of different ways they can be stored. It's not really super critical. But those access tokens remain in your web browser, so when it goes to these dozens of different servers that composite the page that you're looking at, your web browser hands those servers the access tokens. The access tokens know how to read and decrypt them to see what it is you're allowed to have access to and who you are. They don't have to go back to those security guards every time they get a request from you and suffer a whole bunch of delay and latency trying to get into every room that you might access in that social media building, for example.
Can I ask you a question?
Sure.
When a hacker hacks into Facebook and allegedly steals 50 million, are they getting it off the server, the central servers, or are they going into everyone's individual computer to get the access tokens that have been...
They're getting them off the central server. They are not accessing everyone's individual
Okay,
computer.
so it's all right.
And the way that can happen, we'll talk about in a minute. The bottom line is, so I'm going to, in the interest of brevity, I'm going to probably go through this a little bit quicker, but the tool that Ms. France showed you, that showed individual transactions going back and forth, that, yes, between a web browser and a web server, shows the many dozens of transactions that are going by. Oftentimes, those transactions are authenticated on the server side with these access tokens. So there's a couple different types of access tokens. You can have a token that's specific to you, a judge, and it's going to get you into your chambers and into your courtroom and into the areas of the building that are appropriate for you. There might be other kinds of access tokens that are, for example, the people who bring the food to the cafeteria. They may have an access token that's used by that vendor, like without identifying an individual person. It gives them access to the kitchen, and they can put food in the kitchen. You can have access tokens that are for the security guards that give them wide access that they may need in times of an emergency. So access tokens contain within them the permissions that you have to move throughout the building, so that when you present them to a door, that door will open, right? That's how basically that's how the metaphor works for gaining access to all these different elements of data. So one of the problems with access tokens is that they're a bearer instrument. If you've got a token and it's still valid, it's unexpired, however you obtained it, you can emulate the user that's identified within it or use whatever permissions are granted by it. So the question hackers are looking at is, how do I obtain other people's access tokens? So access tokens are protected a number of different ways. When they're transacted between computers, they're encrypted while they're moving over the internet. They're encrypted when they're stored on the computer's hard drive. But they have to be available and open and unencrypted for use when they're, to a certain degree, and there's some inaccuracy there, but when they're inside the running web browser, so that the browser can hand them back to the server. Now there's another layer of internal encryption that the token is still encrypted for you when it's on your browser, when it's transacted back and forth in that list of back and forth transactions you saw in Zap. Your computer never decrypts it. You don't have to be aware of what's in it. Facebook has or whoever the web application is, has the decryption key and the encryption key. They put all of the permissions information and access control lists inside that token. They put the identity information in there. They hand it to you so you can give it back to them. It's just like your access badge. The security guards give it to you. You're giving it to the door or to other security guards as you're moving through the building. You don't have to know what's on the card. You just know what it allows you access to.
And then, Mr. Streeb, could you discuss how one could exploit flaws to obtain access to those access tokens?
Sure. In the metaphor that we've been talking about, if you come into this building and the security guards take your passport and your license, that's a long-term form of an access token. You keep it. You don't use that license to open the door. You use a short-term key card that they give you. In this metaphor, the guards give you a card that's valid for some period of time and for the doors that you're able to open. If those security guards make some kind of a mistake, and some of these mistakes are going to sound a little silly and obvious, and they're not applicable to what happens necessarily in this case. We don't know yet. But for example, if I come in and say to the guard, I need access to room 12, if instead of making me a unique access card that has a very specific permission to open this door for room 12, if they instead said something like, well, here's Judge Alsop's card. He has access to room 12. Just use that. Then I've also got access to everything else that you've done. That would be a silly mistake, and I'm not saying that that's what happened here. But those kinds of architectural mistakes are what occur in these kinds of situations. Somehow, through some method, some architectural flaw or bug in the software, the wrong access token is provided to an end user, maybe through a series of complicated interactions, but hackers figure out how to tease somebody else's access token out of the authentication login servers or out of the web application servers. And they do it by using tools like Zap to examine what's going by and making, educated guesses about what they do to change or what's happening.
And Mr. Strebe, on this, what's now slide 17, we have a photo of the web inspector.
Sure.
Could you just briefly explain what that is?
So this is a picture of a social media website, and this is a regular web browser. Most, if not all, web browsers have special extra tools that are built into them for software developers to use so that they can examine what's happening inside the browser. So right here you see I'm just going to this menu item that's built into my web browser. It's called Show the Web Inspector, for example. And what we're looking at now are actual access tokens. These are embedded in the web browser. They're stored here when you use this site for some temporary period of time. The highlighted one there is, for example, an actual access token. I don't know what it means. That's just a random string of letters and numbers with some dots and dashes in it. I'm not sure what its purpose is without going through some level of discovery, but the bottom line is that's what they look like. This one is this long. The length of them varies depending on how many permissions or access control entries they might have inside them. What's put inside of an access token is entirely up to the web application developer.
And are these encrypted or are these decrypted?
These are, well, most of these are encrypted. Some of them are actually not encrypted, and some of these are not access tokens.
Okay. And in the interest of time, we'll move on to OAuth 2.0. If you could explain for the judge and the court what we mean by OAuth 2.0.
Sure. OAuth 2.0 is the protocol that implements these access tokens. It's a standard that was put together by a web standards body. It's used by a number of different web application sites.
And what's the interplay between latency and security with OAuth 2.0?
Well, so just as with an access badge, there are vulnerabilities to access tokens because they're bearer instruments. If you were to lose your access badge outside in the street and a person who's not authorized to be here wanted to enter the building, and we imagine that the security guards don't know who you are otherwise and trust the bearer instrument that they're handed, then that person can get in. So because it's a bearer instrument, there are these vulnerabilities, and they're oftentimes limited by having a very short expiration time. But that's totally up to whoever writes the software for the web application. It's oftentimes a trade-off between security and ease of use. To make it really easy to use a website, to reduce kind of barriers to growth or barriers to obtaining clients, it makes sense for companies not to do things like pop up a login dialog box every time you start the website. So you might log in once every few weeks or once every few months instead of every time you go there. It makes it simpler and faster, but it leaves a token on your browser that may be somehow taken and used by other people.
What is the difference between these tokens and a password?
So the tokens contain all of the information necessary to gain access to a website without you having to prove who you are. They give you an authority, but they don't authenticate you. The assumption is you've already been authenticated by an authentication service, and the ability to decrypt that token proves that you were authenticated at some point in the past.
And Mr. Strebe, how does that tie in with the view as function that's at the issue of this case with tokens and access tokens?
Well,
without the benefit of discovery, of course.
Yeah, without the benefit of discovery, what appears to have happened is that there's a feature in Facebook that allows you to see what you look like to other people. So, for example, if you have a person, well, I might not want my mom to see all of the same posts that I show my friends because I have different aspects of my life that I expose to my mother than I expose to my friends. So it makes sense for me to know when I post something whether or not my mom can see it. So that view as feature appears to have been implemented in such a way that it would have passed my mom's user token down to me when I'm using that function in certain specific cases. And so one of the problems with OAuth that developers have to be very careful about is that they never send a token to a web browser that doesn't belong to that user. It's a vulnerability that's known about the protocol, and it's something that that developers have to be vigilant about. If hackers were able to exploit a website to obtain a different person's access token and then use that token to see more tokens that belong to other people, then they could repeat that process with an automated script.
Well, take your example. I still don't understand this quite. I understand that you want to show your friends different photos than your mom, but when you do use the view as, how are you pretending to be your mom and using her access code? How does that part work?
Well, so Facebook has their own method of doing this, and I don't want to assert that I know what that is yet. I only know a few things that have been made public that are fairly vague about it, but it appears that, yeah, they're creating, you remember when I mentioned that your web page comes from many different servers and every data element on it comes from different places? It might be a simple way to compose a page for you from somebody else's viewpoint if you were to use their permissions to do it. And that way the page gets assembled in the same manner as it would be assembled for that other person in a very simple way. That's a possibility.
But, so you're saying, literally, if I understand you, that you looking at on your Facebook page would say, I want to do the view as, and then you would type in your mom's name and somehow the computer would use her access code to
It would be safe to do that to some degree if the access token always stayed maybe on some server that Facebook owned and was never delivered to my web browser. But if because of a combination of features or a mistake or something like that, her token was ever actually delivered to my web browser, then it could cause a vulnerability like that.
All right, now, let's be clear, you're just speculating here. You don't know that that's the way it came down.
Right.
Okay, all right.
I'm speculating.
All right.
So I'm saying how these things could happen generally to a web app based on, many different things. So.
All right. You got about 2 minutes left.
Right. All right. So the only, so we do have some preliminary questions that we need to know in order to figure out, really what went wrong. How was the view as token developed? How does Facebook test the security and functionality of that prior to release? What processes do they use to test their features like view as? And in general, what security development processes, practices, and policies does Facebook use to test their software prior to release? When did Facebook first detect this issue, and how did they detect it? When did they identify the root cause of this issue, and how did they identify the root cause? Was any report developed by Facebook internally or by a third party to discuss the issue? And how did Facebook determine who was affected by this? What steps did they take to contain and remediate the issue? Those are
okay. You're getting more into the argumentation here, but all right. Okay, let's bring yours to a close. I thank you very much for your assistance.
Thank you for the
All
opportunity.
right, let's go to the, we'll go to the other side for about, you have an hour or two. We'll probably do about 15 to 20 minutes, find a legitimate breaking point, take a break, and then come back and finish your part. So how would you like to proceed?
Your Honor, I think we just need a moment to switch the technology so that we can load our screen in. Literally just a moment. That was incredible. Your Honor, Andrew Klubach, again from Latham & Watkins on behalf of defendants. Your Honor, first of all, we appreciate this opportunity. We have endeavored to adhere to the questions that you asked about in your order, where you asked us to talk generally about the issues related to this case, and then you identified some specific topics. In particular, you'll see I hope our presentation is designed to go right to the issues you asked. There was a little bit of discussion about some of the specifics related to the case, and as plaintiffs, we're not intending to get into the details.
That's fine.
But there are some general issues, and there are some discussions about Facebook that will be discussed in the general context of security without getting into too much in the details of this case. Although there is information that has been publicly disclosed on blog posts, and to the extent we need to clarify some of the questions you had referring to that information, we're happy to do that. In particular, Your Honor, we categorized or put this presentation to 4 different areas. The 4 areas, broadly speaking, are how do attackers get access to data? What do attackers do with compromised data? How do companies, you said the industry, defend against attacks? And then we talked specifically about Facebook's general approach to security, although without getting into the details of this particular. Now, Your Honor, we have these 4 sections, and it may be after the first one. That will be a nice stopping point for a break.
Sure.
We have 2 presenters today, Your Honor, and the first presenter who will speak to the first subject of how attackers get access to data is named John Milliken. Now, Mr. Milliken works for Facebook. He's a member of the privacy infrastructure team. He's from London, which you'll be able to tell immediately from his accent, I think. And he received his degree in computer science from Cambridge. Back in 2012, he won Britain's Cybersecurity Challenge UK, which was a nationwide competition about cybersecurity. He joined Facebook in 2014, and he spends his time working on building privacy-enhancing features. In particular, recently, he's been working on developing improved approaches for end-to-end encryption, which is one of the specific subjects you asked us about. He works with external groups, including the Internet Engineering Task Force Messaging Layer Security Working Group, which is a worldwide organization that is, in this particular case, working to build protocols for pushing the state-of-the-art in encryption technology. He's authored peer-reviewed publications, including one on authentication and one on encryption protocols. He's spoken at a number of conferences, including where he was a keynote speaker at a conference hosted by Parliament, where he actually demonstrated for members of Parliament how an attack could take place. In this case, it was on the BBC, and he'll talk a little bit about that. And that's his general background. He's going to speak to the first section. I guess I'll hold off talking about the second and third and fourth, because that I think will be a natural.
All right, let's bring him forward.
And Your Honor, maybe it'll be more convenient for him to be at the stand.
That's fine. Again, you don't have to be under oath. This is a tutorial. It is being recorded, though, so it might be used in the future. Welcome, sir.
Thank you very much.
Say your name again.
My name is Jonathan Milliken.
Okay, welcome. Please go ahead.
Thank you very much, and good morning, Your Honor. Thank you for the opportunity today to talk to you about cybersecurity.
Of course.
So I'm going to start by talking about how attackers get access to data. And it's easiest to frame this discussion with sort of consideration of what the fundamental challenges are with cybersecurity that make the field of cybersecurity a little unique. So to start with, the internet is open by design, and this is a good thing, because if you're running a public website, for example, it's actually quite desirable for this to be accessible for anywhere, for your business to be able to reach people who are anywhere. But this does also mean that attacks can be launched from anywhere, potentially by anyone and at any time. And also, because attacks are just information or code that are running, it's relatively easy for these to be replicated across the web and are often automated. Another issue is that when we're talking about complex online systems, the fact that they are so complex essentially means that bugs are inevitable, and some of these bugs can result in vulnerabilities. Because we're talking about code bases with millions of lines of code in which there are millions of potential interactions which can't all be predicted or tested, and particularly as these systems evolve over time, predicting what things may happen in future is with existing code is very challenging. And it's also a very asymmetric enterprise to defend against attacks, because fundamentally, if an attacker has a goal that they want to achieve, they only have to find one way that they can succeed in achieving this. They only need one exploit that can do it. Whereas in defense, you need to be concerned with the entire attack surface of places where these attacks could happen. And so, if we want an analogy for the challenge of cybersecurity, people often think about a safe, but this isn't really a great analogy, simply because a safe, for example, has a pretty specific security goal. So, for example, that only the person with the key can access the contents. You're concerned about a limited number of security properties, for example, the strength of the box or whether the lock can be picked. And it's designed in advance of use. It's not some evolving system. So a much better analogy would be a city, for example, where, for example, there are many different entry points, say by foot, by road, etc., but also perhaps things which aren't designed for humans to enter, say the sewage system. A city is constantly evolving. It wasn't designed at some point. There's always construction going on, for example. And its threats vary widely. So, for example, you may want a country's military to defend it against invasion, but also kind of smaller threats, such as people failing to pay for public transport usage, for example. So it's a much closer analogy with many different entry points. It's evolving, and there are just kind of broad risks, many of them unpredictable. And I mentioned this notion of an attack surface on the first slide. So it's worth briefly defining this. So this is all of the points on a network which might be accessible to an external attacker. And so in a highly complex system, this is likely to be very broad. So for example, if you're running a website, your attack surface could well be the servers running your website, the website itself, the user interfaces that are provided, any developer interfaces that allow third parties to interface with your websites, the email accounts that your employees use, and any other portals which these employees use to log in, and then any other third-party systems that your site may connect with. But that's just a few examples. There are many more possibilities. So let's look at how a few attacks may happen. These examples will all be somewhat simplified, but they're designed to kind of give the rough idea. So this first attack is an attack on internal systems. It's sort of an instantiation of the high-level hacker lifecycle that we saw in the previous tutorial. So this example may, for example, start with a phishing email. A phishing email being an email designed to trick someone into doing something against their interests. For example, it may contain an attachment which is actually malware, so software designed to damage the computer or gain unauthorized access in some way. So in this example, if we have a malware attachment and an employee opens it, then this might give an attacker control of that employee's computer, which can then serve as a foothold into the company's network.
When you say open, do you mean open the open the email or click on the attachment?
Typically these days it would be clicking on the attachment specifically. Generally, just opening an email wouldn't succeed these days, although I couldn't say for certain if that's always the case.
Okay. But let's take that example. When you click on you get the phishing email, and then there's a thing. I know enough not to click on it. I'm afraid to even open them. So, but let's say you click on it. So what happens then if it's malware?
So it depends really, but typically we'd expect it to exploit some vulnerability which allows it to gain access that it shouldn't. I have a few slides on vulnerabilities later on.
Okay. You proceed.
Thank you, Your Honor. So if an attacker has a foothold into the company network, this is now a point where they may be able to gain privileged access. And so this device may already have privileged access, or it may be able to move elsewhere within the network so that they do. And so if an attacker's goal is, for example, to steal data from the company's database, once they've reached a point in the network where they can access this, the malware can simply exfiltrate the data back. I say simply, none of this is necessarily simple, but the compromise, of course, has made it significantly easier for the attacker. So let's look now at another attack, which could be an attack on a web platform. On this slide, we're seeing the attacker is using a website directly. And so this screen, this web interface, is their own computer. And so what might happen is an attacker experiments with a website and they go looking for bugs. For example, potentially using the tool that Ms. France described earlier. And sometimes they'll succeed, and sometimes they'll fail, but sometimes they'll succeed in finding a bug. And if there is a bug, then sometimes these will result in vulnerabilities, which can then be exploited, again, to exfiltrate data back to the attacker. And this could potentially be the same sorts of data that could be accessed with the direct access to the company database in the previous example. But, of course, the attacker in this instance hasn't ever been inside the company network. They haven't gained privileged access in that way. Another potential attack could be an attack at the point that data is transmitted to a user. The previous tutorial discussed about how you mentioned about how connections go through a variety of routers and switches. And so no connection is direct. And so if one of these routers in the middle is malicious, for example, a free Wi-Fi network that you may connect to in a coffee shop, if someone sets one up and you can't distinguish that from an actual legitimate one, then this can potentially mean that when you connect to a website, an attacker can then control and manipulate your connection in various ways. And it's potentially easiest to describe this by way of example of the attack that Mr. Klubach described, that I demonstrated at this conference run by the UK Parliament's ICT Forum a few years ago. And so,
what was that? Are you going to explain that?
Absolutely.
Yeah,
yes.
please explain that example.
So in this example, in the conference before my talk, I set up a Wi-Fi network called Dubious Fake Network, just to make sure that they'd know not to connect to it. But I invited anyone who wanted to participate in the demonstration.
It was called what?
Dubious Fake Network.
Fake?
Yes.
Did people connect to it anyway?
When I invited them to, if they wished to participate in the demo. But certainly I wanted to make it clear to them that this was not something that you would typically want to do. And so I did warn them that I was in control. But this network, it behaved exactly like a normal Wi-Fi network, unless you actually connected to the BBC News website. Now, the day I gave this talk was Halloween a few years ago, and so I replaced the headline that they would see with a story about a zombie apocalypse occurring in London. So in this case, it was obviously fake, but if someone wanted to attack you in real life, it's likely that, for example, maybe they, rather than manipulating the data, they would just observe the data being transmitted and try to steal anything that was sensitive that had been sent. And fortunately, I should just say that the BBC News website is no longer vulnerable to this as of last year.
So you were able to break into the BBC?
Oh, sorry. I should clarify this. At no point did I break into the BBC or access any of their servers. This was just at the point that the website was delivered to the user. So it was happening on the router that I had connected to, rather than in any way damaging any BBC assets.
So someone who was at the conference wanting to tune into the BBC News would get your thing about zombies instead of the real thing?
If they were connected to Dubious Fake Network, then yes.
I see.
But if they were connected to Dubious Fake Network, perhaps they shouldn't have been surprised by that.
I see. Okay.
So finally, I'd like to talk about an attack on user devices. So this is a little different from the previous attacks, because these could be out of the website's control. And so in this instance, let's say an attacker wants to infect the devices somehow. For example, using a phishing email, like in the previous example. Sorry, not the previous, the example that I started with. But then the attacker can either take data from the device or wait until the user, say, connects to a website which they're sending sensitive data to, at which point the attacker can read that data and, again, exfiltrate it back. So you asked about how these attacks may happen, say how malware may take control. And the answer here is really there are software vulnerabilities out there, and these attacks often exploit them. And actually, most of the time, we're looking at publicly known vulnerabilities in third-party software. When you say, if you're talking about a company, you're not talking about their own software, but software that they're running from others.
Wait, I don't understand that point. Say that again.
Within a no company will run exclusively its own software. They run software from a variety of vendors, potentially including themselves. And so any of this software which they're running on their network has the potential to contain a vulnerability. And often these are publicly known. They can be reported in the database called Common Vulnerabilities and Exposures, which is totally public. Thousands of these are reported every year. And typically there are patches available, but often attacks will happen because people or companies have failed to ensure that these patches are actually installed to protect them against these vulnerabilities. So if we look at publicly reported vulnerabilities over time, we can see in the late 90s we were looking at a few hundred per year, but now, say in 2018, there were almost 16,000 of these reported. And this is actually...
Is that new ones per year? 16,000 new ones per year?
Yes. Or just under, yes.
Wow.
And so this is a good thing because these databases being public does help companies to understand what their risks are and understand when they're vulnerability and when they're vulnerable and they need to patch their systems. But it's also very useful to attackers because they're often able to scan for vulnerabilities and see which companies are actually exposed to that threat. But there is another class of vulnerability, which is called zero-day vulnerabilities. And so it's much rarer that an attack will use one of these. And these are named 0 days because a defender has had 0 days of knowledge about this bug before it's used. So having not known about it, they haven't had a chance to fix this vulnerability. It requires sophistication to identify because a company will typically be able to prevent a lot of the low-hanging fruit, for example. And so if no one else has caught them before it's been attacked, then that innately means it's going to be harder to find them. But using them doesn't necessarily require this same degree of sophistication because it's often possible to buy exploits for zero-day vulnerabilities, for example, through criminal networks. And I believe that's the end of this section.
Your Honor, is this the time when you'd like to take the short break?
Yes, this would be a good time. And let's see, you've used about almost 20 minutes. So